Module 27, Nonlinear Dimensionality Reduction, specifically t-SNE, UMAP, and a little bit of manifolds. By the end of this module, you should be able to explain the goal of nonlinear dimensionality reduction and the informal idea of a data manifold. You ought to be able to implement and tune t-SNE and UMAP on small data sets in Python, adjusting key hyperparameters and interpreting their effects. You should be able to compare PCA, t-SNE, and UMAP qualitatively, like high level, relating each method to different analysis goals. You should be able to diagnose common misuses and failure modes of t-SNE and UMAP, even though we won't get into too many failure modes today. And you ought to be able to connect nonlinear dimensionality reduction to broader themes in representation learning and visualization, although this is something we'll be talking about in future modules to a large extent. So we know what dimensionality reduction is. We talked a lot about it in the previous module on principal components analysis. We have data points x in big d-dimensional space, and we want to compress it down into a new vector z in k-dimensional space where k is a lot smaller than d. And we want to do that in such a way that we keep most of the important structure or information in the data originally. So often data can concentrate near lower dimensional surfaces inside R of D. So all of R of D, there's small surfaces inside of R, a d-dimensional R. Locally, like very zoomed in, the surface can look flat like a hyperplane. But globally, it can kind of curve and twist in various ways. And we say that data will lie on or near this k-dimensional manifold. So we have local structure and we have global structure. Locally, we can look at a data point and we can say, who are my nearest neighbors? And then we can try to preserve small distances. And then we have global structure, which is like, where are the big clusters relative to each other? And we want to preserve longer range geometry. So linear methods that just involve lots of matrix multiplication, like principal components analysis, are pretty good at preserving global variance. We're looking at global changes in variance. But they can badly distort local neighborhoods when the manifold, the low-level manifold, is curved, if that makes sense. So this motivates the idea of nonlinear, warpy dimensionality reduction. These are methods that try to unfold curved manifolds and keep nearby points close to each other in the new lower dimensional representations. So a classic example is t-SNE, which is going to directly focus on preserving these local neighborhoods rather than only purely global variance. Here's some code for you to play around with yourself. Not too much is here. This is from, again, sklearn data sets. We're going to see make Swiss roll a lot because it involves like multiple dimensions and nonlinearities. This is the original manifold, sort of this curled up pastry looking thing. And then you have the linear projection. You can kind of see the three-dimensional shape here when we used PCA to convert these 3 dimensions down to 2 dimensions. But kind of some of the surface level structure is lost in 2 dimensions, even though you're picturing this in 3 dimensions. In 2 dimensions, we have all this no overlap now between these purple points and these green points. That shouldn't have occurred, right? Like purple is, according to like the colors anyway, on this spiral, very different than green. So the fact that they've projected onto the same space is a big no-no. So this is a problem we want to solve, and we can solve it with nonlinear dimensionality reduction. This is an example of using t-SNE, which we'll introduce in a moment. We're projecting the high dimensional Swiss roll manifold down to 2 dimensions. Everything's spread out in a way that preserves global structure kind of, but it also especially keeps local structure consistent. So very briefly, linear versus nonlinear dimensionality reduction. We saw linear dimensionality reduction with PCA. This is linear maps, this kind of big matrix W, which we just multiply by X, and this gives us a transformation Z. This is good in unsupervised context especially. It's good when the main structure is roughly linear or gently curved, like these big kind of blobs in space we saw in the previous module. That's sort of like the de facto environment in which we're using PCA. We care about variance maybe, global trends, like big picture stuff. PCA is your tool. But you can't unroll like nonlinear complicated manifolds like the one we just saw. And it'll also often mix these distinct clusters in ways that we just saw a moment ago also. Nonlinear mapping will open up all kinds of new possibilities. We still want a mapping of x onto z. We still want a lower dimensional z, like 2 dimensions. Often this is implicit, like we don't have to actually learn the mapping explicitly. We're going to try to preserve local neighborhoods. The data points close to each other should stay close together. And also usually approximate global geometry. t-SNE and UMAP are the two methods we're going to see in this module. These are primarily used as visualization tools. I know PCA, we talked about like explanation and all kinds of other reasons we'd use PCA. t-SNE and UMAP are really just about visualization. So, you know, in a research paper, you might have some fancy looking graphs and look how great our model is. Like t-SNE and UMAP are good for those purposes, but you know, there's risks to using them as well. So we'll talk about that in a moment. So the core idea is pretty simple of t-SNE. If 2 points are close in the high dimensional original space, they should end up close together in the 2-dimensional plot. And if they're far apart, the algorithm doesn't really care that much about their exact distance. So there's a few steps. In the original space, we're going to turn distances into probabilities of being neighbors. This is the kind of first conceit. We have this probability model. What is a probability that these 2 points are neighbors from each other? So for each data point x sub I, we'll produce this little tiny distribution over other data points. So how likely is x sub j to be a neighbor of x sub I? So here's just like a Gaussian looking thing. It's an exponential of the square differences. So it looks like little Gaussians around points. And then we'll have the width of this Gaussian is sort of the perplexity parameter. So basically how many neighbors each point is allowed to care about. That's this beta. This can be like any number. It can also be literally just an effective number of neighbors. But normally it's essentially the width of, like generally it's going to be the width of this Gaussian that we're centering around a data point x sub I. And then this Gaussian, I mean, it's a kind of fake Gaussian we're using to pretend it's a probability, but it'll kind of give us like a pseudo probability that point x sub j is a neighbor of x sub I. So the second step is just to symmetrize to get these joint probabilities. So, you know, the probability of I being a neighbor of j and the probability of j being the neighbor of I should be similar to each other or identical. So we want to make these symmetric. So take it as read that that's what we're doing. And third, in low dimensions, in the 2-dimensional, for example, embedding. Actually, usually t-SNE is used in 2 dimensions because it's going to be used first for visualization for humans, unlike PCA, which can be used for 2-dimensional representations but doesn't need to be. Anyway, in 2-dimensional representations, we're going to put down these new points y sub I and define another set of probabilities q of I sub I j. And we're going to use this heavy-tailed student's t-distribution instead of a Gaussian. This just basically means faraway points will get a little bit of probability mass, and that's basically it. This is kind of hacky, but it works. So then we're going to choose, step 4 is basically moving the 2-dimensional points around so that q looks as much like p as possible. Okay, so we want to just move things around so that q and p are similar as possible. There's lots of measures you can take to look at the similarity between 2 distributions. The Kullback-Leibler divergence is one of them. We're not going to have too much time in this course to get deep into what KL divergence is, but it's defined this way. It's not symmetric, so it's sort of like given an encoding defined by Q, how close is the distribution P to the distribution Q. So we have 2 distributions, P and Q, both defined by distances of points. We just want these things to be as close as possible, so we move points around to make them as close as possible. So this is sort of a iterative, slow process, potentially slow process. So optimization is going to be done with gradient descent. The details don't matter to us right now. They can be from a random initialization, so all of the probabilities, everything's totally random, or you can start with PCA to get your initial like embeddings, but we'll see examples of each of these in a moment too. So for the same data, we're going to get 4 different embeddings. We're going to see the 2-dimensional PCA, using methods we saw in the previous module. And then we're going to see 2-dimensional t-SNEs with different settings for perplexities. Remember, perplexities was just that little hyperparameter on the Gaussians for our distribution P that tells us how many neighbors each point cares about being a neighbor of. So small perplexity means very local. I only care about the neighbors that are absolutely closest to me, and that means clusters can be fragmented, more likely. Large perplexity means that you have a wide range of neighbors, which is good if you live in a society, but maybe not so good if you're looking at t-SNE. And then, obviously, usually the best thing is a balance between the extremes. So medium perplexity is a nice compromise. So then all we do is, again, all the details are hidden from us now, but basically, these are the high-level details. And then you get these visualizations. So in PCA, we also have different digits. So this is, again, the digits data. I can't remember where I loaded it. I think I just loaded it here, actually. Yeah, so I just load the digits here. So this is the good old-fashioned digits data set we saw in previous modules, digits 0 through 9. We can do the projection like we saw in example 2 from the previous module. Everything's kind of mushed together, right? This actually results in good classification. So it's a bit of a cartoon example. But then you can see t-SNE, when it cares about clusters, it cares about similarity. So even without doing any kind of machine learning yet, t-SNE already kind of splits the data in a way that produces tighter separated digit clusters in a way that PCA doesn't. So you have all these zeros over here in the upper left, the 3s over here in red in the upper rightish. And as you increase the perplexity, these clusters become more fine-grained, more tight, which is kind of what we like, right? So this is the difference between a t-SNE and a PCA. So when you see a paper or you see a visualization of a representation of data, if it looks kind of like this, usually it's a safe bet that it's a t-SNE. And often they'll just also cite that original paper by Madden and Hinton anyway. So why does t-SNE love local structure? So we can look at the cost function. The cost function, like when we're doing the optimization, is the KL divergence. We're going to keep on trying to change, the Qs so that P and Q is as close to each other as possible. This is like a one-sided divergence, so it cares a lot when P is big and Q is small, and it almost doesn't care when P is tiny. So the interpretation is if 2 points are close in the original space, that means P is very large, but we map them far apart in 2 dimensions, so Q is going to be small, then the loss is going to be huge. The gradient says nope. These 2 points are not, we need to pull those together, right? Like P is, in P, original data space, these data points are close. In Q, they're far, it's bad, bring them together, right? The divergence is too big, bring them together, right? On the other hand, if 2 points are already far apart in the original space, so the P is very small because the probability of these being neighbors originally is very small, and in Q, it's also very small because the probability of them being neighbors in the new space is very small. Maybe it's medium distance, maybe it's super far apart. 2-dimension barely changes the loss. The optimizer doesn't care. It's a bit more free to shuffle the clusters around a little bit, if that makes sense. So that's basically it. This is kind of tells you why is t-SNE obsessed with local structure. It works hard to keep local neighbors together. Neighbors in the original space, try to keep them together. But if the clusters are far apart from each other, I don't really care. P is small, Q is small, do what you like. You end up kind of with this weird looking, diverse looking positions of clusters. Like the clusters are going to group in ways that don't necessarily make any sense to us. And that's fine, but it explains 2 things we saw in the previous plot. It shows tight, well-separated digit blobs. So we've preserved local neighborhoods of data points from the same class, but the exact layouts of the blobs is 3 close to 8, as we might expect. Maybe, maybe not. We don't care. We shouldn't try to overinterpret too much. So these are the things you need to know, like the details. Again, we skipped over them to a large extent. You'll need to know perplexity. So perplexity basically is that beta value that changes the number of neighbors that every point cares about. We showed like examples of different versions of that in the original graph. Smaller is local structure. Big, you have bigger neighborhoods. But this might end up merging small clusters too. You need a learning rate. I skipped over this, but because we're doing gradient optimization, you have a learning rate. So just like in previous versions of gradient-based methods, small little learning rates means it's a very slow walk to convergence. Very large learning rates means that you might overshoot and have these weird artifacts when you're trying to learn. I mentioned you can initialize either randomly or with PCA. PCA is a good way to kind of like stabilize a low-dimensional representation of the data. It doesn't fix all the issues, but usually initializing with something kind of smart is usually a good thing to do. Random seeds, so different seeds, like we use 3151 as the seed for this course for some reason, but if you use different seeds, you might end up with very different graphs, right? So sometimes people just show you a graph and say, look at this t-SNE. This is the t-SNE representation of the data, but they don't know what they're talking about. Different seeds can give you very different representations. So just be curious or skeptical of what you see, okay? So t-SNE is good for visual exploration. Like it's a good way to kind of do some sanity checking to make sure you're not doing crazy things, but it's not a feature extractor and it's not a very good way of explaining a model. And this is described a little bit in this paper, for example, how to use t-SNE effectively. UMAP is a different method. So UMAP, sorry, I should fix this. This is a reference here. It's in the BibTeX, which I'll fix up before I post the slides. You can assume the data lie on a manifold, like we talked about manifolds before. There's a certain local dimension and there's a metric, and you can approximate its structure with a weighted graph. Then you have this low-dimensional embedding that preserves the graph as much as possible. So the key steps are, for each point, find its k nearest neighbors, same idea as t-SNE. Use distances as edge weights in these tiny little graphs. This is a fuzzy connection strength between data points. And then combine these into a weighted, undirected graph. That's the first high-dimensional graph. You have a low-dimensional graph of points in 2 dimensions, usually, maybe 3 dimensions if you're feeling frisky. And then you define this fuzzy graph in the embedding. And then you optimize by minimizing the cross-entropy between the high-dimensional graph and the low-dimensional fuzzy graph. And then basically, again, similar to t-SNE, push pairs together that should be strongly connected, and weakly connected pairs, you can push them apart. The hyperparameters here are very similar. We have a number of neighbors that are, in a graph structure, how many neighbors do you connect to? This is, again, a trade-off between local and global structure, just like in t-SNE. Small number of neighbors emphasizes very local neighborhoods. Large, you capture more global structure, but clusters are less separated. And you have minimum distances, how tightly points can pack into a cluster. Small, tight clusters, large, spread out clusters. UMAP ends up being a lot faster than t-SNE, and it scales better to large data sets. This is not always going to be the case, but it's often going to be the case, and you can read more about dimensionality using UMAP in single-cell data here. Another anti-example, suppose you run t-SNE on a patient embeddings from an ICU data set, and you see a big blue cluster of patients who survived and a small red cluster of patients who died, and the red cluster appears very far away from the blue one. So this happens sometimes. You see this in real papers that are published. Not this exact example, but ones like it. They say, well, red is very far away from blue, so these patients are fundamentally different, and the model has discovered a clearly separable high-risk subgroup. So the issues here are that the distance between clusters in t-SNE, but also in UMAP, are not metric distances. This isn't a measure. There's no measure in these dimensions. The layout can change dramatically with the hyperparameters being changed or even the random seed. And again, run the code yourself and see how different things are on each run as you change things. The rotation, the reflection, the location, all of these things don't change the cost of the optimization functions for t-SNE and UMAP, but they can result in very different visualizations. So just like a very positive metric on a classification result can appear very meaningful, you have to run them over and over again to see how things actually are changing to make any claims like the one we made a moment ago. So you really want to dig into the data itself, not necessarily these t-SNE or UMAP visualizations to come up with your conclusions. And again, you should run classification metrics, look at ROC, area under the curve, calibrate, do held out test sets, do all the good science that we've been hammering home throughout the other modules. t-SNE and UMAP can be supporting visual evidence. Like we put that in a paper to say, here's an example of a t-SNE that we produced, but not the only one we could have produced. There's lots of other t-SNEs we could have produced, and don't hyperfixate on that. Always check robustness, do the science properly. This is a visualization more than, it's not explainable AI, it's a visualization. Some quick examples. I want to compare PCA and t-SNE on the digits data set. We saw the digits data set previously. Actually, we saw this even in this very same slide deck. We're going to use the same low digits data set. We're going to subsample for speed. We're going to do some standardization. This is all in the code here. I'm using a pipeline. I'm not using a pipeline here. Shame, shame, shame. I'm using just step-by-step a standard scalar, and then I'm using PCA and so on. This is this PCA. I have two components. I have taken my 64-dimensional data and I've boiled it down to just 2 dimensions, and I have the explained variance ratio of the first and second. We kind of talked a little bit about this very vaguely in terms of sigmas and singular values in the PCA previous module, but this is that's as maybe. And then this is the visualization. Nothing very fancy. Here I'm calling sklearn manifold, and I'm importing t-SNE, and I'm just calling it. It's a very simple function. I have 2 components. My perplexity hyperparameter I'm setting to 30. The learning rate will be automatic. The initialization will be random. You can change this to PCA, and my random state is provided. And the net result is this little visualization here. Isn't that nice? So in the table in PCA, the first 2 components explain a very small amount of the total variance. The only, using only this 2-dimensional PCA collapses lots of digits together in a way that's not really acceptable. I get a big blob of a lot of different classes here that all kind of mix together in a way that might make classification difficult in 2 dimensions. From these plots, clusters might be a little bit separated. The 6s down here are quite different than the red 3s over there. But the directions are linear combinations of pixels. Directly, the structure is global through maximization of variance. t-SNE, given that these are different clusters, we tend to get more compact clusters, but the shape and the relative position can change with the hyperparameters, so be careful. A PCA is still useful as a linear baseline. I think sometimes people think that, well, because we're learning a t-SNE thing using something fancy, well, kind of fancy like Kullback-Leibler divergence, it must be better. And look, at these clusters are all nicely separated from each other. But I mean, they're kind of solving different problems. This is not exactly apples and oranges, but PCA is doing other stuff apart from just visualization, and t-SNE is really focused on visualization first. So of course it is, quote, better. Anyway, I'm not bitter. So example 2 is a Swiss roll we saw before. Show how nonlinear dimensionality reduction can uncurl these things. We saw an example of this before too. Now I'm using this data frame. This is my hyperparameters. So I have perplexity for t-SNE. I have number of neighbors for UMAP. And I have this extra hyperparameter for UMAP as well. That's all I'm doing. I'm passing these into again, not a pipeline. Again, it's not really a pipeline appropriate, but I have my original data. I make the Swiss roll. I get my principal components analysis like I've done several times at this point. I get my t-SNE like I did using the t-SNE function we saw a moment ago. UMAP is a little bit tricky. You have to make sure it's installed in your system, as you generally have to do anyway, or you have sklearn, but UMAP there's a library called UMAP. It has this UMAP function. Here are my hyperparameters, which I've defined previously. And then I just graph everything. Here's the result. Here's my 2-dimensional unrolling of the Swiss roll, my t-SNE representation, and my UMAP representation. The difference between t-SNE and UMAP might not be too obvious from this kind of point of view. So why would I use t-SNE or UMAP in this case? Well, PCA can flatten the rollout and still leave overlaps. I mean, it doesn't leave an overlap here in this case, but it did when I saw the visualization earlier. Nearby colors can be folded over each other. There's all kinds of problems. t-SNE generally produces an unrolled band, so there's not much overlap. The global shape can be distorted. Here, actually, the t-SNE and the UMAP still kind of, I can still, see generally this kind of band-like structure in each of these things, so there's not much of a clear benefit of one over the other. UMAP tends to unroll the manifold, but these hyperparameters can really change with how much of the global structure is enforced and how tight the band is in terms of close neighbors. So nonlinear dimensionality reduction can reveal latent low-dimensional structure, but the exact appearance will depend on these hyperparameters, random seeds, and all kinds of things. So just be careful and don't take a single t-SNE graph as if it's the golden truth from on high. Some quick evaluation checks. So again, dimensionality reduction can be kind of an exploratory visualization tool, but you should play around with the seeds and the hyperparameters, compare against baselines. PCA remains a very motivated, theoretically valid, strong baseline. Just because it's older doesn't mean it's necessarily somehow deficient compared to this learning-based method. You want to do quantitative sanity checks, so you might want to dig into classification accuracy and trustworthy or continuity metrics. So all the same kind of good machine learning science we talked about before still apply here. t-SNE, UMAP don't tell the whole story. The point is still doing prediction. The point is still doing prediction well, moreover. So t-SNE is sort of a nice visualization, but it's not the main meal. And also check for reproducibility. This actually goes back to multiple seeds and hyperparameters, but make sure that environments can be regenerated as much as possible. And remember that pretty pictures don't replace proper model evaluation or held out data. Don't get dazzled by flashy lights. So can we have ethical concerns with regards to nonlinear dimensionality reduction? Well, yes. So sometimes you might overclaim a structure like we saw with patients before, that doesn't really exist. You might see that there's clusters in the visualization that aren't as obvious in the real data. Is this a visualization trick? It's a trick of the light, as some might say. So be careful. Again, looking at minority groups, sometimes rare subgroups can be collapsed or scattered or subsumed by bigger clusters. They can be hard to see. So you have to make sure you're being responsible in that sense and still do good science. Don't just cherry pick hyperparameters that give you the prettiest pictures. Without transparency, without doing this carefully, this is essentially p-hacking for plots. So like trying to get the prettiest plot is not really good science. It's not very ethical. The regular mitigations apply. Be transparent, provide all code, provide all data that you can, and so on. Curiosity, I'll leave to you to check out on your own. Here's a quick check as usual. Here are the references. As usual, it's been a pleasure. Thanks so much. See you next time.